Welcome. And so welcome also from my side. I didn't plan to say a lot. I really look forward to this week speaking about structure in imaging, sparsity, and learning. All of us are now trying to get our heads around how we can integrate learning components into what we have done so far. And so I look forward to seeing what all of you are thinking about this along these lines. And yeah, our first speaker this morning is Jim Nagy from Emory University. And Jim will speak about spectral computed tomography. And I think I should set you up with...
How's that?
Yeah, okay.
Okay, you can hear me okay? All right, well, thanks very much for the introduction, and thanks a lot for the invitation to be here. It's an honor to be here and also to help open the workshop. This project is joint work with several people. There'll be a few other people I'll acknowledge along the way. But these are the ones I'm currently working with on this project. So Martin Andersen is at the Technical University of Denmark. Yunyi Hu is a PhD student at Emory. Yannis Sakopoulos was in the Department of Radiology at Emory University's medical school. And this is where we got interested in this work, was through Yannis. And he moved recently to the Netherlands. And Jun Zhang is from the University of Shanghai. He visited me for a year recently. And of course this work has been, I want to acknowledge support from these various institutes. All right, so let me just start basically at the end. Here's the problem that we want to solve. And so basically we have a nonlinear inverse problem that we want to solve. So here, of course, X is going to represent my unknown stuff, and I'll tell you what that stuff is in a minute. And everything else is known, or I should say at least approximated. We can approximate the rest of the stuff, except the noise. So the idea is, of course, given my projected data and a lot of different information, can I reconstruct whatever this X is? So we'll set it up as a nonlinear optimization problem. So we'll need a fit the data term and a regularization term as usual, and then we'll have some a constraint set where we'll put our solutions. So I'm going to do something quite simple, but you can change your fit to data if you like. So we're going to use basically a least squares fit to data term. We're going to use the simple Tikhonov regularization, but we can replace that with your favorite regularization if you like. And this set Q, and you'll see where this comes from as I talk about the model, basically is a very simple constraint set. There'll be certain values that will sum to 1 in here. And then also we'll have a bound constraint here as well. All right, so let me just tell you the rest of the story. So that's where we're going to end up, basically. So I want to tell you how I get there. So the original motivation was from Yannis Sakopoulos in radiology on breast imaging. So I want to tell you a little bit about that. And then the mathematical setup, we'll look at both the X-ray source and X-ray tomography problem that we want to look at. So there's an X-ray source and an X-ray detector, and there are various physical quantities that you want to try to represent there. And we'll talk about how to make the problem maybe a little bit simpler, and then talk about the optimization, some numerical examples, and conclude. All right, so probably most people here know what tomography is, but let me talk to you about it in the sense of breast imaging. So typically, mammography is a sort of standard technique used in breast imaging. In the United States, when women reach the age of 50, they go every year for a mammogram. And so it's recommended that they should. And so the way it works is that the breast is put into a compression plate. An X-ray, of course, is taken of that, and so you have a detector here. And so the X-ray, of course, passes through the object, whatever it is, and it attenuates as it passes through. And that the amount of attenuation, of course, depends on the initial X-ray energy. If I have a very low energy X-ray, of course, it's going to attenuate a lot, maybe not even pass through, depending on what the material of the object is. So it has to depend on both of those quantities. The detector, of course, measures the attenuation of that projected data. And in mammography, that's just an X-ray, right? It just you display it as an image, a two-dimensional image, and it looks like an X-ray image. In tomography applications, of course, you're going to then take multiple projections. So you would take multiple projections around the object, and then, of course, try to reconstruct a 3D or a pseudo 3D reconstruction of the object. In tomosynthesis, this is a term used for just limited angle tomography. And I'll show you a machine that, where this does this in a second. But it has very limited number of angles that it does. And of course, you can have full CT, which would then take projections all the way around the object. All right, so here's two machines that were at Emory. I say were because this machine now is in the Netherlands. But this is a typical situation that you would see for a mammography or a tomosynthesis. So the patient, so this is where the technician stands. The patient stands up against this machine, and there's a compression plate here. There's an X-ray source up here, and then, of course, a detector. And, of course, a single mammogram machine would look something like this, and they would have a single X-ray and produce a single picture. In tomosynthesis, they put the X-ray device on a little gantry. You can see this little gap here, right here. So it's allowed to rotate back and forth, plus or minus a certain number of degrees. It's actually quite limited on how much it goes back and forth. So maybe plus or minus 15 degrees only. Right? So from there, you then try to get a pseudo 3D reconstruction of the object. In full CT, the patient has to lay down on a bed, and there's a hole in the bed where the breast is laid, and then there's the CT machine is in this round thing down here, and then it circles around. There are, of course, advantages and disadvantages to these different technologies, of course. So in tomosynthesis and mammography, the disadvantage is that, of course, you get lower resolution because you have less data to work with. The other disadvantage is that the breast has to be compressed in a plate, which is, can be uncomfortable. On the other hand, the machine is quite small compared to the CT machine. It takes up a lot less space, cheaper to construct, and the mammography machine sort of made into a tomosynthesis machine is a small change in some sense to the machine. Of course, tomography will give you a better resolution, but of course the machine is bigger, and it's not as easy to climb on top of this bed if you have mobility issues and so forth. All right, so those are the two different machines. So let's talk about the mathematics of it. Most of you have probably seen this before. So the projected data that you receive at the detector is modeled as some integral stuff here. So you have some unknown here is really what you're looking for. Is the energy, excuse me, dependent attenuation coefficients of the object. It depends on where in the object it is, and of course the energy at which the X-ray is emitted. So then as the X-ray passes through the object, it goes through on a line integral, and you integrate, and then there's this energy-dependent spectral distribution function that depends on the source X-ray. So we need to know what that is. And so energies at which the X-ray is emitted depends on the kind of material that you're trying to image. For medical imaging, especially for breast imaging, they try to do a very low energy X-ray, but the energies could just depend on the object and the source. Of course, you have a number of pixels in the X-ray detector, and I'll give you specific numbers of these things later. And then the number of projections. As I said, in tomosynthesis, you have a limited angle, very few projections, and in full CT, you'll have many projections. Of course, you have your noise, which can comprise many different things, such as X-ray scatter and electronic noise. All right, so let me just say something about the unknown. So usually we represent this in this thing. I'm writing it down as this mu here is my unknown. It's the attenuation coefficient. In medical imaging, you can write these down as either linear attenuation coefficients or mass attenuation coefficients, depending on what information you want. For us, it's not going to really matter much, and I'll talk a little bit about this later. But in any case, either one of those unknowns is going to depend on the material in which it goes through, and also the X-ray energy at which the X-ray is emitted. For a 3D inhomogeneous object, of course, you have different materials all throughout the object. So then, of course, the attenuation coefficient then depends in some sense on position, where it is in the object, because the material is different in there, and then also the energy at which it's emitted. All right, so if I have a full homogeneous object, it's all one material, of course, then the attenuation coefficient is only going to depend then on the energy. And the nice thing about this sort of simple observation, if you like, is that you can do tests in a lab and say, okay, what are the attenuation coefficients for a particular material? And this has been done, and in fact, the US NIST website, you can get attenuation coefficients for whatever material that you like. Okay, so you can figure this out. All right, so this is just to show you a plot of these things. This is for calcium, this is iodine, and this is adipose tissue. And this is how the attenuation drops off, depending on the X-ray energy at which it was emitted. In many cases, you'll have this thing called a K-edge that you'll see. Depending on what the material is, where that K-edge will occur will depend on the material. All right, so let's get back to the mathematical model. So again, I have projected data and my unknown here, and then the rest of the stuff I'm going to assume is known, except, of course, the noise. If you discretize this, of course, the integrals become sums. You have the sort of weighted attenuation coefficients here, some of those, and then you have your spectral distribution function here as well, discretized. So this matrix here, of course, you can think of it like a radon transform. It's just basically the length of the ray through whatever voxel it goes through. Of course, I'm going to have a number of voxels that I'm going to discretize my object into, and of course, the number of energies at which I want to discretize my spectral distribution function. So in matrix vector notation, this would look like this. I would have a single, think of it as a single projection. My theta is a single angle, so I haven't changed any angles yet. I haven't rotated anything yet. And so I'll have this single projection. And so I have this sort of matrix vector multiplication here. This exponential function is, of course, element-wise exponential. So I have this guy right here. Now this M here I'll talk a little bit more about in a minute, but basically this is my attenuation coefficients. So each column of this is going to be represented by a volume, and each, so as I move from one column to the next, it's going to depend on the energy. So I have a volume of attenuation coefficients for energy 1, a volume of attenuation coefficients for energy 2, and so forth. All right, so the discrete model, of course, I need many angles, right, if I'm going to do tomography. So I need to project these things, and of course I'm going to get several projections of these things. And the model is obvious, right? I just stack all of these guys up into a single sort of vector and matrix, if you like. So it will look something like this. So this will comprise all of my projected data, and then all of my sort of projection matrices. But I have, of course, the single set of attenuation coefficients at each energy, and of course the single sort of spectral distribution function here, discretized version. All right, so again, this guy here is quite large, right? So it's a number of voxels in each column, and then of course number of energies going across the rows. So it's quite a lot of data to reconstruct. So typically, and of course it's nonlinear as well, right? So my unknown is inside this exponential here, and there's no way to sort of pull it out, unless I assume that I have a single energy for my X-ray. So I'll call that monoenergetic X-ray assumption. And if I do that, of course, then I have one energy level, right? So if I have one energy level, then the spectral distribution function is discretized into a single value. It's a scalar. So that makes things nice. And of course, also this guy right here is a single column, right? It has only one energy in it. In that case, of course, then I can sort of divide out this scalar here, take a log of both sides, And this is typically what's done for most situations. So it's the kind of model that you would use, that vendors would provide with the software in their machine to do the reconstruction. And they would do something like filtered back projection or maximum likelihood method or something like that. Okay, so that's the typical assumption. The problem with this assumption is that the X-ray energy is not constant. And in fact, the X-ray distribution function, that S function, looks something like this. And so this S is not approximated well by a scalar, right? So if I tried to take the average energy, I could think about doing that. Of course, if I could confine my energy bin between some really small interval, then I might be in good shape for this as well, but that may not always be easy as well. All right, so this monoenergetic assumption is quite nice numerically, of course, but physically doesn't really represent what's going on. So the full polyenergetic model is what I would call this. It takes into account those spectral distribution at multiple energies. And again, I have this guy is going to be quite big in terms of my unknown. So if I have a 3D volume that I reconstruct, each column is the number of voxels in it, and then of course number of energies that I want to discretize along that way. Of course, the advantage is it provides more accurate reconstructions, reduces these things called beam hardening artifacts, or these streaking artifacts that you see often in reconstructions. But of course, it's computationally more expensive because this is really a nonlinear problem that you need to solve now. All right, so a variety of people have worked on various things. I just wanted to point out that the first time I got interested in this work was actually when Julianne was still at Emory, and Yannis Sakopoulos was in our Department of Radiology there, and he came to us and asked us about this polyenergetic reconstruction problem. And I have to say that Julianne really took the project and started it, so she deserves most of the credit for getting us going on all of this. And then it sort of continued with some of my additional PhD students. Veronica was another PhD student, and Yunyi now as well. Okay, so the next thing I want to talk about, so all of this has everything to do with the source X-ray. So how do I model how the energy of the X-ray comes out of the source? The next thing I want to talk about is how do I model things at the detector in some sense. So what I can do is say, so forget about the source for a minute. Suppose I grab a bunch of projections. So I do this and I get a bunch of projections and I put them all together and I do a reconstruction. What I might do then is then do the same thing but change the energy at which it's being emitted. So the blue is a single, can be thought of as a sort of a distribution of energies coming out. And then I change it. I increase the energies or I decrease the energies at which I want to emit my source. So the source changes what's coming out, but the detector, of course, then gives me different information as well. All right, so we get two sets of information. And so if I put all those together, I really have, in some sense, more additional information. Of course, the sort of ray trace or radon transform matrices, in some sense, repeat themselves, but the attenuation coefficients change because the energy levels have changed. And of course, the spectral distribution function changes as I change the energies as well. So I get this additional information. All right. So I can put it all together, and I can then go back to the source and say, well, let's assume whether they were polyenergetic or monoenergetic. And things get easier, of course, in monoenergetic, but I can also do the polyenergetic model there as well. All right. So the disadvantage of this, of course, is that I've just doubled the radiation dose, or actually maybe even more, depending on if I increase the energy to the patient. So I have additional radiation dose to the patient, and that actually could be significant. So, but the idea of doing this was actually, proposed in the 1970s. I mean, this is an old idea, right? It makes sense to think about doing this. And the original idea was to think about how do I separate bone, how can I tell in the image if I know where I have bone and soft tissue. You might look at it and say, okay, I can see from the pictures, but quantitatively you don't have any information that tells you this. So this was the idea of this, to try to give you quantitative information so that you don't have to look at the picture to tell you the information. Okay, so a variety of people have worked on this. As I said, this is to do quantitative imaging, to tell me what is the material in the object if I can. Especially if there's only two main tissue materials in the object. of course, there's an increase in radiation to the patient. So how would you reduce the radiation dose? So you might go back to it and say, well, instead of repeating all of the energies, I might say, let me just do a few of them at a certain energy level, and then switch to another set of energy levels. And that way I've gotten basically the same radiation dose to the patient as I would have with one set of energies, but additional information as well. All right, so that's one idea, of course. And again, you can think about the source being polyenergetic or monoenergetic, doesn't really matter. Of course, you could then do something quite different, right? I could sort of alternate the two between two different energy levels. There's lots of ways to imagine this, right? And these are the kinds of things that physicists are, you know, so Yannis is a medical physicist, and it's the kind of thing that he's interested in understanding. What is the optimal way to do this? Of course, you could, of course, change these all different energy levels, right? Now, engineering-wise, I don't know how you make it work without, you know, the machine has to be able to do this real time. But in any case, these are the kinds of things, theoretically, we would like to understand. Okay, and again, we can model the source in any way we want to. This is sort of detector information that we're trying to get. Now, when you put this together mathematically, you say, okay, what does it look like if I put it together? So if I have different energy levels, right? So these S's are spectral distribution functions. This is one set of energies. Then I jump to another set, and so forth and so on. And if I can do this at the source and completely separate it at the detector as well, then of course things just decompose very nicely into sort of like a block diagonal system. Now, physically doing this, where I can actually separate those things completely, is probably not possible. There should be some bleeding between the X-ray emission, and so you're not going to get quite a block diagonal system out, if you like. So there'll be some overlap there as well. All right, so that's sort of how you might think about it mathematically. But in any case, when you put it all together, the mathematical model is quite similar to what I already wrote up in sort of the general form. I'll come back to this in a minute. So I do want to mention something about energy discriminating detectors. These are really important devices that are being investigated these days. And they actually can, in the detector, I'm not an engineer, so I don't know precisely how it works, but at the detector level, they can separate, they can get measurements from different energy levels, right? So they actually, you don't have to repeat the experiment. You have a set of energies coming out of the X-ray, and the detector then bins it into different energy levels. Now, that's not an easy engineering feat to do, and so discriminating between them is not necessarily perfect. So typically in medical imaging, when you have sort of low energy X-rays that you're using from the source, typically they just bin them into high and low, whatever high and low means to them. Right? So you get a high-low, low. So that's like a dual energy measurement, if you like. In other applications where you can, you know, you do these not live objects or objects that you don't care stay alive, you can hit them hard with high-dose energies, and you can do these in much more bands. So the reason this was important to us is that, as I mentioned, one of my collaborators, Martin Andersen, is at the Technical University of Denmark, and in their physics department, they have an experimental detector that actually does this, and they just blast, you know, inanimate objects with high-energy X-rays for a long period of time to gather all of the information. All right, so let me come back to the basic mathematical model. It all looks like this, basically. You have this term here where I have my attenuation coefficients. As I said, again, each column of this is a volume, and as I go across their energy levels, and I have the spectral distribution function. I'm assuming these guys are known, and my attenuation coefficients are the things that I want to reconstruct. That's a lot of information to reconstruct, and so oh yeah, so I wanted to just say something about in the limited angle case of tomosynthesis, a typical detector will be 1024 by 2048. So they're pretty high resolution detectors. Now, because it's very limited angle, they don't ask for a lot of resolution in the Z direction. So you get something like this. Now, if you were to go to full CT, the detector would be less refined here, so I don't remember the numbers, maybe 1024 by 1024, but then of course you would have in the Z direction much more higher resolution. All right, so of course though, now if I'm going to do this for each volume, and then I have a number of energy levels, the number of unknowns is quite large, depending on how fine you want to discretize your energy levels. All right, so to reduce memory requirements, what we decided to try to do at first, this was our first motivation for it, was to reparameterize the problem. So we said, okay, if my object is made up of a certain number of materials, and I know what those basic materials are, I may be making a guess, I may not know precisely, but I make a guess, then I'll say, okay, maybe reparameterize it in terms of materials rather than in terms of number of energy levels. Right? So the nice thing about this is that you know attenuation coefficients for pure materials. You can look them up in a table. You can get that information if you like. And so you can then reparameterize it. So it would look something like this. My attenuation coefficient might look like a linear combination of known, so these C's are the attenuation coefficient of a pure material, whatever that pure material is, at different energy levels. Okay, so the attenuation coefficient of a mixed set of materials then would be a weighted sum of the various pure materials that I expect to see in my mixed material, if you like. All right, so that's something there. Now, of course, you might ask the question, is it really a linear combination of those things? And that's a great question, and the answer is probably not, but you have to make an approximation somewhere. It's easy to see that if the densities of the materials are quite similar, then this linear approximation holds quite nicely. All right, so I'll talk a little bit more about when it doesn't hold in a minute. But in any case, if I write this down, this is really like a matrix-matrix product where I have a known attenuation coefficient. The transpose is just for convenience sake, so don't worry about the transpose, just a matrix there, and another matrix. And these are matrices, this matrix has weights in it. Right, so now how many weights does it have? Well, it has, in some sense, number of volumes. So I still have a number of voxels, but then I'm going to go by number of materials. And if I have, say, 3 materials, then I only have sort of 3 volumes of storage in some sense that I need to keep. All right, so then I write it down. It looks something like this. So I replace my attenuation coefficients with this weighted stuff of known. And here, of course, now the W's are the unknowns, and everything else I assume known in here. Now, of course, if these are true weights, they're fractions of material, and so I can assume that these weights sum to 1. What? Oh, so if I have, okay, so it's a great question. Why? So if I have a certain number of material and I say I assume it's broken up into, say, 5 materials, then I would assume that there's a percentage of 1 material, percentage of 2 materials, and percentage of 3 materials, and they should add up to the 1 material that I have. Now, I may be missing something, so that assumption may not be quite correct. Right? So if I say you're made up of bone and soft tissue, so 100% of you should be made up of bone and soft tissue. So I should have maybe X% of bone and Y% of soft tissue, and those things should add up to 1. Yeah, they're weight fractions in some sense. All right, so as I said, this idea of using these known attenuation coefficients here is assuming that my different materials have similar densities. If they don't, we should try to take density into effect, and that's where the mass attenuation coefficients come in. So the rho here represents density, and so what you can do then is, of course, then write your mass attenuation coefficient, or your linear attenuation coefficient, in terms of your mass attenuation coefficients, which incorporates density. Now, in this particular case, if I write down what this thing looks like, it's a weighted sum of these guys are unknown in here. So I don't know the density of the sort of mixed material, and I don't know what the percentage is of in the object. So when I put these two together, I have this sort of weird weight here. So here I can't assume that these weights sum to 1 because they're not really weights. They're sort of weights incorporating densities in here in some sense. Right, but I do know these guys here. So these are mass attenuation coefficients that you can get, again, from looking them up in tables, and you can get this material. All right, so, but again, the model looks quite similar. If you see, all there are hats in here. So from the previous model to the next model, I just have hats in there. So they're just, again, stuff that I don't know and stuff that I know, and that's the reconstruction problem that I want to solve. Okay, so something like this. Now I'm going to rewrite this thing to make it in a more convenient form for writing down derivatives and things like that. So what I'm going to do is I'm just going to notice that, so my unknown here is W, and I'm going to change W to the letter X because I like X for my unknown. And then I'm going to vectorize it, so it's a vector of unknowns. So as soon as I vectorize it, I see a Kronecker product in here. And of course, I need to be careful about how this is really a matrix in here times a vector, so I need to be careful about how I do all that. In any case, all I'm going to do is rewrite it in terms of vectorized form, and there's going to be some Kronecker products in it. So when I do that, and I'm also going to change W to X. Okay, so sorry about the change of notation, but that's what I'm going to do. So the problem looks like this. And my fit to data term is what I showed in the very first slide of the talk. So I have those Kronecker products in there. My unknowns, these are my weights. Okay, so those are the things that I'm going to look for. And then, of course, I have this, this S here is my spectral distribution function, a discrete version of it, if you like. So this is what we're going to try to solve, and we're going to use Tikhonov regularization for all of these things. And I should say that you know, I'll write down this constraint set, and I'm putting EG in here, so it's going to depend on the particular model that I want to use. So if I use linear attenuation coefficients, then I might want to make sure that the weights sum to 1. If I'm using mass attenuation coefficients, I might not want that in there, and I might want to have different bound constraints in here, maybe just a lower bound on them. Okay, so that's the problem I want to solve. And so let me look at the Hessian of just of the fit to data term. Again, it's a bit messy, right? So if you look at this thing, right? So I have this x is inside this element-wise exponential. So I need to write down the derivatives, and of course the usual thing is to write it as the sum of two terms, right? So one of these terms is associated with my Jacobian, and then there's the other stuff here. Well, you can write it down, and you can actually compute these things. There is an issue, of course, right? So this thing could be indefinite, so you have to take into account that if you're going to try to use the full Hessian. But you can write these things down. I'm going to try to use both of these things in some numerical experiments to do my solves. All right. So and again, so I'm going to write this k of x to be to sort of shorthand notation for this this function of L here in some sense. Okay, so I'm going to try two different approaches to solve this problem. One is to use a nonlinear interior point method. Right, this is an old paper, but I think a quite nice paper, which uses a sequential quadratic programming trust region dogleg projected PCG approach. And I'm also going to use this projected Gauss-Newton scheme that Eldad has nicely outlined in his book, Chapter 6. If you want to read it, it's a great book to read. Makes great gifts for holidays and Christmas and all those sorts of things. All right, so let me do a first numerical example here. So in the first numerical example, I'm going to set up a simulation for the breast tissue. So I'm going to do two examples here. One is breast tissue because that was our original motivation. The other is to do an example associated with the stuff that Martin Andersen is interested in at TTU. I'm going to do both full CT and limited angle. Now, I'm doing this limited angle is actually not so limited compared to what really needs to be done in tomosynthesis. So in tomosynthesis, typically it's plus or minus maybe 15 degrees only, not 45. So, so I'm not being quite honest to that kind of application, but let's just see how it works. I'm going to play with the regularization parameters. You can ask me how I choose them, and I don't have a good method right now, so we're just going to play with them until we get a good regularization parameter and see what we get. And I'll use this interior point method to solve the problem. All right, so here's the simulated tissue that we did. So what I'm going to do is, and it's only a 2D problem so that we can run lots of experiments on it. So what we're going to do is we're going to have two different materials. So this is one material, and this is the second material. And this sort of simulates what a breast tissue might look like. So you have the blue means the material doesn't exist, so there's no glandular tissue in this part of the object. But there is materials with it in there in the yellow, so that's all glandular in there. And then in the turquoise region is sort of 50% of each material in there. And of course this guy will be just complete opposite, so I'm assuming there's only two materials in my object here. Right, so they should look just a flip of each other if you like, and the turquoise should be in the same region. All right, so let me solve this thing. So let me do the full CT reconstruction on it. And of course we added some noise as well to this. And we solved it via the interior point method. And you get quite a, so if you look at the difference between the two, it does quite well in a full CT reconstruction in separating the material. So it tells me when I get these two, if you like, these are the weights in some sense of the materials. So it tells me I can look in this, I can put my cursor on that location in the object and say, what material is in there and what percentage of material is in there? Can you tell me that? And that's the idea of this sort of quantitative imaging. Now full CT is a little bit easier than limited angle, so if I just go to the plus or minus 45 degrees, I don't expect to do as well. And so you can see that that's true. And you should expect not to see so well. The typical thing though is that you would think about looking at line plots in here, because if my X-ray source is up here, I might have good resolution in sort of the sort of horizontal direction, but not in the vertical direction, because I'm only taking a few angles back and forth up here. So you should really look at line plots. I don't have those up here, but that would be another way to compare these things. All right, so but in any case, it still does pretty good, I would say, in terms of the number of in terms of the fact that we have such limited angles. So you can go back and forth at these things and look at these things, right? So there's that and that. I don't know whether you like it or not, but I think it's not so bad. All right, I did want to say something about the optimization in here. So we have to use some scaling in the objective function. Otherwise, the Hessian solves are quite expensive. In fact, the scaling really makes a big difference in the early sort of Newton iterations in terms of trying to reduce the number of CG iterations there. But this is probably well known to people in the optimization community. So let me come to the second example, where I'm going to set up a different kind of example. So this is going to be two different materials again, but it's going to be plexiglass and PVC. And we're going to do now an energy discriminating detector, simulate that. This is again to try to simulate what they're getting at DTU in Denmark. So we have these different bins, 5 different bins for our energy discriminating detector. I'll assume a polyenergetic source, and I'm only going to do full CT in this particular reconstruction. And again, I'm going to choose regularization parameters just by experimentation, and then I'll use this projected Gauss-Newton scheme. And before I get there, I want to talk about this, the Hessian solves for these things. So you have this, so we're just going to use the Jacobian in this case. So if I look at this guy, I need to solve linear systems with this. And we're going to use, of course, a conjugate gradient method on it. And so what I want to do is I want to precondition this thing. And so the preconditioning is a bit challenging. So everything in here is fixed at each sort of Newton iteration or Gauss-Newton iteration, except this diagonal matrix here. And D depends on my function, my exponential function, and so forth. So it's a bit complicated. But in any case, there's a diagonal matrix in here. So what we're going to do is there's nice Kronecker products in here, right? And so Kronecker products could be put together nicely if they were all Kronecker products. But the problem is that D is not a Kronecker product. So let's just replace it with a Kronecker product by doing an approximation. So I wrote an equals here that should not be an equals. It should be an approximation. And it's not hard to find that approximation. It's a pretty simple thing to do. So I'm going to find this approximation here. And then I'm going to replace that guy with this Kronecker product. And once I do, then I have all these Kronecker products that are going to be thrown together. Now the nice thing about this is that this first term here is actually quite small. It depends on the number of materials, if you like, here. So this guy is a quite small matrix, and I can do lots of things with it. So I can easily compute a Cholesky factorization, whatever you want to do with it, and essentially invert this guy without any trouble. This guy is still quite large in here, and it's a typical thing you might see in optimization with your matrix here that doesn't change, and this thing in here, this diagonal matrix in the middle that does change. So we don't have really a good way to deal with this just yet. So what we decided to do for now is just to approximate it by a diagonal matrix. So we're going to take this, whatever this guy is here, exactly, and invert it, and then take a diagonal here and invert it. And that will be our preconditioner. All right, so let me show you some pictures. Here's our simulated object, if you like. It's plexiglass with PVC in it. All right, so the white is all plexiglass, and no PVC, and this stuff here is PVC, so you see PVC here. And so we do the full CT reconstruction here using Gauss-Newton, and we get something that looks like this. Now, it's not perfect, of course, right? So there's this gray region in here which doesn't quite get it. I don't have the exact, I should have put the color scale on here. But still, it does separate the materials quite nicely in some sense. There's this mixture in here, of course, that's getting noise corrupting in here, but still it's, I think, quite nice. Let me show you, in some sense, the results from using preconditioning. This was the reason, at first we didn't think about using preconditioning, we were just going to run it, right? So we did. And the number of CG iterations that we were needing at each Gauss-Newton iteration could be quite a lot. So we decided to think about the preconditioning, and we came up with this, which seems like kind of a relatively simple idea, but it actually is quite effective at reducing the number of CG iterations at each outer iteration. And I think we were quite happy with that. So we could go back and try to, so as I said, there's this piece right here you could try to do a bit more with, but I think based on our results, the simple precondition was easy to compute, it's easy to apply, works quite effectively. So we were quite happy about that. All right, so I'm going to conclude. I know I'm finishing early, but we started early as well, so that gives us more time for coffee or questions or yeah, tomatoes to throw or whatever. So I think these polyenergetic source and multi-energy detectors they're computationally challenging to deal with. And in fact, for the full 3D problems, you can't just write the code in MATLAB and run it. It just doesn't work. And in fact, even writing a C code and running the full polyenergetic problem is not really a viable way to do it. You really have to write parallel codes for these things. But they can compute quite much better reconstructions and potentially give us more information about the material, some quantitative results. So as I said, for the real 3D applications, it really motivates using parallel architectures, and in particular, I know everybody wants to use GPUs for everything, but this is really a nice application for it. So what makes it worthwhile? Well, if your GPU memory is big enough that you can hold a certain number of volumes, right? So I have a volume for material 1, a volume for material 2, a volume for material 3, and if I can hold those all within my GPU memory and do all of my function evals and derivatives in there, I can make this run quite efficiently. I shouldn't say I can. Those who write the GPU codes can. And so this really, we have a GPU code that we're using for it now for the real data reconstructions. And I think this material parameterization really is what makes it possible, because I've reduced the number of volumes. If I were to not do the material parameterization, I would have to keep all the energy levels in the memory as well, and so that would be not possible. So I think these GPU implementations are quite nice. The people at Radboud are using them on real reconstructions, both for full CT and tomosynthesis, and they seem to be quite happy with the results they're getting. So I'll end there and say thanks very much.
Thank you very much. Great opening talk. Questions?
In a real data set case like mammography, breast imaging.
Yes.
How many different materials did you assume in your?
So we've done 2 and 3. So one of the things you would do in breast imaging is you would do adipose and glandular. You could think about combining those as one material because they're quite similar, or you can keep them separate. The other thing you might include in there is calcium. So if there's calcifications that you find, that's a sign of cancer. But the big thing is to introduce iodine tracers. So they would inject iodine into regions, and so iodine would be a very distinct material that you would do. So that's actually what they would prefer to do, is to use iodine as a third material. No.
Yeah, so concerning the multi-energy case, what are in a way the best theoretical results how to choose these energies and also?
I don't think there are any theoretical results as far as I know. Right now they're just sort of experimental. Yeah.
You have another question?
Yeah. So maybe another question. I mean, concerning the regularization. I mean, did you also try other types of regularization, or?
We have tried things like total variation and so forth. I think one of the things that would be you can have you can envision having material-specific regularization. This I think is the right way to go. So, for example, in breast imaging, as I said, if you have calcium in there, they would be hopefully not too much in there, right? So it would be sparse in some sense compared to everything else. Otherwise, the patient is in big trouble. So you would hope that it's sparse. So you could put a sparsity constraint on it. So you would regularize maybe the material corresponding to calcium as a L1, and then you could do total variation on something else. So we've used total variation, and we haven't seen much of a difference between that and Tikhonov regularization. But it's probably going to depend a lot on the kind of objects that you're reconstructing.
Just a quick question about, since you have multiple channels in spectral CT, right? So would it make sense to try to use some structural similarity across channels?
It might. We haven't done that, but yeah. I think it would be interesting to try.
And related to that, when you can use structural similarity, could you also think of undersampling all of the individuals strongly?
I'm sorry, I didn't understand. Sampling?
Undersampling the CTs.
Undersampling.
I mean, for example, if you think there are people thinking about using spectral in cardiac and doing it over time,
yes,
and you want to reduce those.
Right.
Benefit of the spectral layer still.
Yeah.
I mean, somehow if you have like 5 spectral layer with a fifth of the angles, it should be comparable to a full CT somehow.
Yes. I don't know of anybody doing that, but it would be interesting to try, sure. Okay.
Can this be validated against clinical real data?
That's a great question. So can it be validated against real clinical data? And in fact, part of working with somebody in a medical school is to do that. So Yannis Akopoulos is several, he still has NIH, U.S. National Institute of Health grants to do patient case studies. So that's complicated for, of course, someone like me to do. I don't have access to patients, and I don't know how to do that, but they do. And so they have real radiologists who will read the scans based on the reconstructions that we're doing and the reconstructions from the standard machine that are doing, and then try to then see whether they're able to do better with false positives, false negatives, better detect cancers and things like that. So these studies are going on, yes.
When you apply preconditioning method,
Yes.
Relative error, since we are using approximation, maybe there is a difference between non-preconditioning method and preconditioning method. So relative error becomes larger and larger when we are using the preconditioning method with the approximation.
So the preconditioning, of course, is on the inner solve, right? And so yeah, I'm not sure I understand the question. So the relative error is,
When I saw the paper, the relative error is more for preconditioning until iteration 4.
yeah, I mean, so this is stopping at the fifth Newton iteration, right? So this is the relative error at the outer iteration. So if I run more iterations, of course, it's hard to decide precisely when. And so I'm looking at relative error of truth, and so there's a stopping criteria, of course, there that depends on residual in some sense. Yeah.
Okay. Thank you very much.
Okay.
Again.